Hey everyone, it's Bradley Bush with another algebra video for you. Today we're talking about compound interest. Compound interest, I like the topic because I like money. I mean, who doesn't like money when it's not a pain to you? So the first thing we're talking about is the definition of compound interest. We've got two formulas and we'll talk about both of them. The second thing is we'll do kind of a comparative analysis. So we'll give an example with both of these formulas and see which one is better. I'll also put the times stamps for each of these parts in the video description, so if you want to skip ahead, you're more than welcome to. All right, compound interest. What exactly is compound interest? What does compound even mean? It sounds like something from a movie where people try to get away from society. We have two formulas. Let's talk about them piece by piece. Let's kind of break them down. I've color-coded them so we could talk about their individual parts. So let's start. So let's say t is our variable in our equation, and t represents time in years. A is the account balance after t years. So say we put money into a bank, and they're giving us a certain interest rate, and 5 years down the road, we're like, how much money is in our bank now? That would be A. R is the annual interest rate in decimal form. That's really important. When we're using percents in calculations, we almost always use their decimal equivalent. So we're using the interest rate in decimal form. And P is the principal, or in other words, the initial amount we put in the bank when time equals 0, t equals 0. So say right now we're putting money into the bank. We put down $1,000, and then 5 years later we come back and say, hey, how much is there after the 5 years of accruing interest and compounding? Well, P, which would be the initial amount, would be the $1,000, and A would be the amount above $1,000 that we had because it had been sitting there getting growing interest with interest. So now that we have all those pieces, we can discuss the two following compound interest formulas. The first compounds n times per year, and that is A equals P times 1 plus R over N, all raised to the nt power. That's n times t. So what does compounding n times per year mean? Well, what is compounding anyway? Compounding is the process of the bank, for example, if you have your money in your bank, giving you interest on the money that you have lent them, or in other words, put into the bank. So say I say I want to put my money in some type of interest-bearing account in the bank, and the bank's like, hey, I'll give you 2% interest if you just keep your money in this account with us. So you put in $100, and they say it compounds one time a year. So you put it in, and you start out with that $100, and then after a year, they're like, okay, you've had it in here for a year, so now we're going to give you, I'm going to write this down here so you can see it. You start with $100, and after a year, this is year 0, here's year 1, they're like, hey, I guess we should give you your 2% interest because you've had it with us for a year. So they give it to you, and now the $2 is added, so now you have $102. That process, and then for the next year, you're building interest on the 102, which is your principal plus the first year's interest, not just the original $100. So that idea of you getting money from your interest and it going with your original amount, that's called compounding. So every time you compound, the bank gives you the interest money it owes you, and it goes into your account, and your account gets bigger. So the more time you compound, the more times you compound, the better for you, because that just adds to the chunk in your bank account that's earning interest. So you want that. You want lots of compounding if you can. If you compounded continuously, meaning you never stopped, you were always compounding, then we would say n goes to infinity. And n, again, is this variable here. So if If we have a finite number of times, say we compound monthly, then n would be 12, and we'd put 12 here for the n in both of those spots. But say we want to compound continuously, that's a really good scenario, right? Because we have lots of compounding, good for us at least. Then our formula would change to a equals p, e, which is the exponential, the natural exponential function, raised to the r times t. R and t are both in the exponent. So those are the two formulas, the compounding n times per year and the continuously compounding formula. Now, let's start with a scenario. All right, here's your example. We're going to invest $8,000 for 6 years, and you've got two options. Your first option is they say 7% per year, which is a pretty good return from a bank. Compounded monthly. You're like, okay, sweet. Next option is 6.85% per year. Well, it's not as good as a 7, but this is compounded continuously. So the continuous compounding is better than the monthly compounding, but the interest rate is lower than the monthly compounding. So how do you know which one to choose? Do you go with the better periods of the more periods of compounding, or do you go with the better interest rate? Who knows, right? Well, let's figure it out. So option 1, 7% per year compounded monthly. And again, we're putting 8,000 down. So here we're going to put in our principal then is 800. That's what we're starting with. And we have 1 plus, what's the interest rate? 7%, and we use the decimal form, 0.07. N is the number of times it compounds per year, and it's monthly, so there are 12 months in a year. And now we do 12 times, what is t? How long do we have this in? 6 years. So there we go. Now we've got to take this and plug it into a calculator. And we hope I remember it once we plug it into the calculator. So we have 8,000 times 1 plus 0.07 divided by 12, all raised to the 12 times 6. Let's make sure I did that right. 8,001 plus 0.07 divided by 12, 12 times 6. I think we got it. Enter $12,160 and 84 cents. 12,160.84. That's approximately 12,160 and $84. That's not bad. We start with 8,000 and we had it in there for 6 years, and we got over 50% return. That's not bad at all. Let's see what the other one is. Option 2, 6.8% per year, compounded continuously. So lower percent, but we have more periods of compounding. So let's see. Let's see if this works for us. All right, we're using P, which again, 8,000. And we have E, which is the exponential function, and R, 0.0685 times what time? Time is 6 years. Let's see what that is. 8,000 times E to the 0.0685 times 6. Let's make sure we got that right. 8,000E 0.685 times 6. All right. 12,066 and 60 cents. That's interesting. $0.60. So which one gave us more money? That was $12,160 and 84 cents. And then we had $12,066. So we got about $94 from the higher interest rate. So even though option 2 had more compounding periods, which in general gives us more money, the difference in the interest rate was big enough, the drop was big enough to not be able to overcome the deficit, even though we had more compounding periods. So there we go. We should choose. Well, which one would you choose? I know which one I would choose. I want the one with more money. Option number 1. So we'll choose option number 1, which gives us $12,160.84. Hopefully this was helpful. If it was, if you enjoyed it, please subscribe to the channel, give me a like, and thanks for watching.